to that in a minute. But there are many, many ways of choosing bases. Essentially, you take the eigenvectors of any Hermitian operator will form a basis. And in particular, if we're interested, we may be especially interested in energy eigenstates. For example, a particle in a box that represents a box. The horizontal axis is the position. The vertical axis is the potential energy. When you get to the edge of the box, the potential energy becomes huge, and the particle just reflects off. It can't get through. In that case, the ground state wave function looks like that. The first example, we'll call that psi1 of x. The next energy eigenstate looks like that. We'll call it psi2 of x. And these are basically signs. Sign of two nodes, and they're characterized by the number of nodes. Rather peculiarly, I started with psi1, which has no nodes. Psi2 has one node, but so be it. Psi I of x. These are supposed to be energy eigenstates. They're orthogonal to each other. They form an orthonormal basis. So let's write the equation for that. The equation for that is that integral of psi star I of x with psi j of x, that's the inner product, dx. What is that? Anybody remember? Delta ij. If I is equal to j, they're the same state. The inner product is one normalized state. If they're different, they're orthogonal, corresponding, let's say, to different energies. Sorry, delta ij, not zero, delta ij. That's another fact. Now I'm going to show you another little manipulation. This one, yeah.
Why does the probability density have that particular form?
That goes back to the postulates of quantum mechanics. The postulates of quantum mechanics says that probabilities, here's psi of x. This is the inner product of psi with a state localized at x. It's called the probability amplitude. The postulates of quantum mechanics, which I invite you to go back to, they're in the book, say that the square of that is the probability. So, okay, here's a little trick, a little mathematical trick that occurs over and over again. Take your orthonormal, your favorite orthonormal basis of functions. They could be sines, they could be cosines, they could be harmonic oscillator wave functions, whatever. Some collection of psi's which are orthonormal. Okay? And if they're orthonormal and they form a basis, then if you take this object, what is this object? This object is a operator. It operates on a state. Let's see what it does. Let's just explore what it does when it acts on a state. What does it do? If it acts on a state psi, then the beauty of the Dirac notation is you can just take the formulas that you've written down here. When you act with this thing on a state, psi with I is a number. It's the inner product of psi with I times I. That's what it does. Now, here's a fact about any orthonormal basis. If you sum over all elements of the orthonormal basis, in other words, in this case, all the energy eigenvectors up to infinity, then what do you get? The unit operator, I, the identity operator. The operator that when it acts on any vector in gives you back the same vector. That's a marvelous theorem. It's in the notes, and you should go back to it. Don't take my word for it. You can prove it, but it's a useful thing to know. Okay, let's use that now in the following way. Let's take a project. Let's act with this thing to the right and to the left. What we're going to do is we're going to take. What we're going to act. What are we going to act on? We're going to act on a state to the right, which is localized at position X. And on the left, we're going to act. Well, actually, what we're doing is I'm taking the inner product of a state with a particle at X with a state at Y. Everybody know what that the mathematical symbol for that is? The Dirac delta function. But let's come to that for a moment. Let's not write that down yet. Let's write that is equal to the sum on I, Y, X. Now all I've done is plug in the unit operator here. That does nothing. But now I have a formula here. The inner product of I with Y is psi I of Y. Let's see. Yeah. The inner product of any state, an eigenvector position is the wave function of that state. Here the state is I, and it has wave function psi I of Y. Here's over here, psi I of X. And what does that have to equal? It has to equal delta of X minus Y. Sum over I. Yeah, there is. The second one. Yes, the second one. I assume that's what you were asking me. Yeah, the star. Okay, now we have a marvelous theorem. If we take any orthonormal basis, they could be the eigenvectors of any Hermitian operator, but in particular the energy, and you multiply for each one of those states, psi star times psi, and then sum over them, you always get a delta function. That's a good thing to know, as we'll see. It's useful. It means there's many, many ways of writing a delta function. Just take any orthonormal basis and do this. These could be sines and cosines. Sines and cosines are another way of writing a delta function. But, and this is the basic mathematics. No more mathematics. That's it, I think. Okay, now let's come back. Let's go to the problem of studying many particles all at the same time. Okay. Now, how are we going to characterize a state? One set of states which is particularly useful is a set of states in which you say how many particles there are with each one of these energies, for example. How many particles are there with state psi 1, psi 2, and psi 3, and so forth. And so we can take the multi-particle system and characterize it by a basis of states, which are just N1, N2, dot, 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 and I, dot, dot, dot. The N's are the occupation numbers. They're the occupation numbers which tell you how many particles there are with each energy level. Okay? And those are states. They're not single particle states. They don't even belong in the same vector space with the single particle wave functions. The single particle wave functions are themselves a whole vector space. But we're now talking about a bigger thing, a bigger system, and so we should not confuse the single particle states with the more general structures that we're talking about. We use the same notation for them because nobody ever invented a better notation than Dirac's, Bras, and Ketz. But, okay, next, we would like to be able to change the number of particles. Maybe we do or maybe we don't want to change the total number of particles. That's not clear yet. But we'd like to be able to change them, and so we'd like to be able to raise and lower the ends. So we introduce an oscillator for each eye. For each eye we introduce an oscillator, and at the moment this has nothing to do with oscillation. This is just a trick. This is just a bookkeeping trick, although it will be more than that later. For each one of these eyes, we introduce a creation operator or a raising operator. Let's call it a creation operator since it's now going to create a particle. A creation operator and an annihilation operator. And the creation and annihilation